We are discussing organic chemical technology course module 7, and I have given the introduction of petrochemical industry, how the evolution of the petrochemical industry that has taken place, and what are the development that has taken place in the petrochemical industry, what are the various feedstock in petrochemical industry, and how the refinery and the petrochemical complexes that can be integrated for more value-added product and to improve the economy of the refinery. Today we will be discussing one very important part of the petrochemical industry, that is, you can say, the heart of the petrochemical complex, that is naphtha and gas cracking for the production of olefins. This is the typical, you see, the naphtha cracker plant, and which is having a number of furnaces, and I will be discussing in detail about this the naphtha cracking and the gas cracking, because you see the what has happened in case of the coverage of the lecture, that will be introduction, naphtha gas cracking, hot section and cold section of the cracker plant, main reaction involved in the naphtha pyrolysis, operating variables in the steam cracking, operating severity and selectivity, typical steam ratio in cracking, upgrading performance of the furnace, what are the development, various development has taken place, because you see the from the initial stages of the coming of the petrochemical, there is a lot of the changes in the furnace design from horizontal to vertical tube, and then the low capacity to the high capacity with high residence time to low residence. These are the some of the development to reduce the run coking in the furnace, to increase the run length. These are the, and then to better more and more flexibility of the feedstock for the. These are the some of the development that has taken place in case of the recovery furnace. So, we will be discussing what are the various measures that has been taken for upgrading the performance of the furnace, decoking and run length, because that is very important, the run length of the furnace, and so the because that is unavoidable to, because the carbon always the coke formation is there, only thing by properly operating and using of the some of the inhibitor that we can reduce the coke formation, and then the, as I told you, the development in the steam cracking and the furnace. Why cracking? You see, the I discussed while discussing the raw material for chemical process industry, and that was the we started getting ethylene through the molasses route from the ethanol. But you see the importance of the ethylene, that is a major raw material for the petrochemical industry. So, the olefin, ethylene and propylene are major building blocks for petrochemical and are used for manufacture of polymers, chemical intermediates, synthetic rubber, and a large number of other products. Olefin includes ethylene, propylene and butenes. Again, because in case of the cracking process, or even in case of the FCC, C4, C5 hydrocarbons are also produced, and so the recovery of those, that has become very important. Ethylene, because that is the major product, sometimes we call it ethylene cracker also. So, ethylene is the king of the chemicals, mostly used in large number of the petrochemical processes. The global ethylene capacity is 1.138 million tons as on January 2011. Steam cracker, major source of the olefins. As you see, the in case of the we discussed earlier the FCC, there are two major sources of the olefin, especially the propylene. One is the naphtha cracker, another is the FCC. Already we have discussed about the FCC and in detail, and so I will be not discussing that part, but recovery part again we will be discussing in while discussing the propylene. So, let us discuss about the some of the aspects of the naphtha cracking. So, olefins are major building blocks for petrochemical because of their reactivity and versatility. Olefins, especially the light olefins like ethylene, propylene, butenes, there has been tremendous growth in the demand of these olefins. The steam cracker remains the fundamental unit and is the heart of any petrochemical complex and mother plant, and produces large number of the products and byproducts such as olefins, ethylene, propylene. Butadiene is a very valuable product we are getting from the naphtha cracker plant. Butane, butenes, isoprene and pyrolysis gasoline, that is one of the complementary steam that we are getting byproduct, which is rich in the aromatics, or after the it can go for the production of the after the pre-treatment, remove the sulfur compounds, it can be used for the separation of the aromatics foam along with the reformate. These are the some of the actually the company's top ethylene complexes involved, which are making a large amount of the ethylene and propylene. So, modern ethylene plants, let us discuss in detail about the naphtha steam cracker. Actually, the basic feedstock for the cracker plant is your naphtha and the natural gas, means the ethane and propane portion. So, modern ethylene plants incorporate following major process steps: cracking, that is the hot section, where the cracking of the naphtha or the natural gas that is taking place, ethane propane, compression of the gases and separation of the cracked gas by low temperature fractionation, because the temperature of methane is boiling point is -165, and so the low temperature that has to be maintained for the separation of various olefins and the other gaseous components which are being produced from the cracker plant. The nature of the feedstock and the level of the pyrolysis severity largely determine the operating condition, the cracking and the quenching section, because you see in case of the, suppose if you are having the heavier even the gas hull, that can be cracked, but what will happen in case of the gas hull? The complexity of the separation that increases, because more heavier fraction we are getting rather than getting the olefin. So, the level of the severity means the temperature, because at what temperature we are, because the in case of the gas, lower temperature that will be required if you are going for naphtha higher, and if you are going for gas hull still higher. And now we are also talking about the gas cracking or even the cracking of the crude oil. But only thing, the complexity which I told you, the separation of the process, because in case of the more and more heavier feed, we will be getting more heavier products like pyrolysis gasoline, less olefins. This is the olefin feedstock, which I told you that the, if you see this figure, this is around naphtha share of the feedstock is around 52 to 55%, that is the major share is of the, and rest the ethane and propane, that is also around 30 to 40%, and that is the, because the availability of the natural gas. And at the same time now because the shale gas is coming in a big way in US and the Canada. So, the ethane propane, because the whole process that is going to, because earlier it was not possible to get the shale gas, it was the only after the development of the your horizontal drilling, it has been possible to get the shale gas, and so with the coming of the shale gas in the future, ethane and propane, that is going to be a very valuable feedstock for the cracker plant. Others are the gas oil that may be there. So, this is the how the butane that may be also cracked, but the mostly the ethane and propane part is going to the, because what we are doing in case of the natural gas, we are separating the lighter fraction and the heavier fraction, and after the fractionation only the ethane and propane that is going to the cracker plant. Ethane and propane that can be used separately, or it can be combined, ethane and propane feed that will go to the cracker plant. This is the how the feedstock variation in the furnaces are there, but still the naphtha cracker. So, while discussing the cracking plant, we will be discussing the process which is being used both for the gas cracking or the naphtha cracking. Only difference in case of the process it is that in case of the gas cracker, first major operation that is there, the separation of ethane and propane, and then the ethane and propane that is going to, then after that the cracking and the quenching, separation of the products, all those things, that is the same process that we are using. So, the naphtha, the gas cracking, that is why I am writing both the naphtha and the gas cracking. There are two sections, one is the hot section, the feedstock is paralyzed and the effluent condition. This is the, because here the high temperature that is required for the cracking of the feedstock. So, the next section after the your effluent, that is which the product you are getting from the hot section, that is immediately quenched, that will be discussing why we are doing the quenching and all those things. But the effluent is condition, separation of the heavier fraction that is there, then it is going for the gases, that is going for the compression, for removal of the impurities, means the H2S and other CO2, that will be the, and moisture that will be removed from that, and after that will go to the cold section of the cracking plant, where the separation of the various steam that will take place. Hot section, hydrocarbon feedstock is preheated and mixed with the steam, that is also preheated. That is what we are doing in case of the, it may be the hydrocarbon feedstock, means it may be naphtha and the ethane, propane, both that may be there. So, the even you see the new furnace which was started by Reliance, that is the multi-feed, because normally in many of the cases, even in case of the fertilizer, what we are doing, we are going for the multi-feed, because in case the gas is not available, at least that plant can be run with the help of the naphtha, or in case of the naphtha is not available, then the natural gas. So, the Reliance naphtha cracker is the multi-feed. So, hot section means hydrocarbon feedstock is preheated and mixed with the steam, that is also preheated. Then the rapid rise in the temperature is taking place in the convection zone, because two sections are there in the upper part and the lower part. So, convection zone, rapid rise in the temperature, pyrolysis reaction takes place, and the final reaction, the both the convection radiation zone that is taking place. So, rapid rise in the temperature is there in the convection zone. This is the actually the typical, you can say, I was telling about the furnace, where you are having the convection zone, naphtha along with the steam that is going there, and the radiation zone. This is the furnace, because the very different type of the arrangement of the tubes that may be there. After that it is going to the quenching, indirect quenching, then direct quenching, and finally it is going for the separation of the heavy ends, gasoline, which will go for the hydrogenation, means that will go for the, that can be combined with the reformate for production of the aromatics, or it may go the high octane pyrolysis gasoline, that will go to the rest of the cane, even that can be used as a fuel also. And the light end, after the compression, the top product of this, that will go to the further separation, that is the cold end of the furnace. Here the steam and the other parameters are playing very important, the temperature, residence time, quenching, all those things that we will be discussing in detail in the next few slides. So, this is the hot section of the cracker plant. As I told you, the amount of steam required, that will depend upon the, even the temperature, that will depend upon the type of the feedstock you are, even the product, which type of the product you are going to get from the furnace, that will depend upon the type of the feedstock you are processing. So, the you see the, in case of the ethane, if you see the figure, ethane, propane, naphtha and gas oil, the requirement of the steam is higher in case of the gas oil, lowest is in case of the ethane, propane, then propane, and then the naphtha. So, actually what is happening, even the cracking, during the cracking, if you are cracking only ethane, it will be higher percentage of ethylene will be there. Both if you are ethane and propane, then the propylene will be also there in appreciable quantity. Naphtha, both the ethylene, propylene and C4C5. And if you are cracking the gas oil, then the more pyrolysis gasoline will be produced and less lighter component that will be produced. So, this is about the steam requirement. Similarly, the cost of the plant, total energy cost and the total cost of the plant, that is also in the same way that is varying. That is, the for the ethane, the energy requirement is minimum. In case of the naphtha is higher than the ethane, propane and the gas oil is still high. So, the same pattern that is also we are getting while we are manufacturing the synthesis gas for the production of the ammonia. So, the radiation zone which I was telling about the hot section, there are two sections, one is the convection zone and another is the radiation zone. So, radiation zone, the hydrocarbon feed is like preheated and mixed with the steam, that is also preheated, rapid rise in the temperature that takes place and pyrolysis reaction takes place. Quenching, that is very important, as I told you that the temperature, if it is going high, the chance of the actually the formation of the coke, that will be more. To avoid subsequent reaction, because the steam is reaction after the quenching, that has to be stopped immediately, and for that, this is the reason why we are going now for the shorter residence time in the furnace. So, to avoid the subsequent reaction, the effluents are fixed in their kinetics development by sudden quench, indirect quench by water to 400-500 centigrade, and which we are using for the steam we are generating, that is used in the system. So, this is the indirect quench that we are doing in case of the cracking plant, because that is very important quenching, because the transfer line, what will happen if the more and more coke formation is there, then the run length that will be reduced. So, this is the why the quenching immediately to avoid the polymerization reaction which may take place if the longer residence time is given, or the if it is not quenched immediately, that will be there, and so avoid that we are doing the quenching direct and the indirect and the direct quenching. Thermodynamics and kinetic assay of the pyrolysis impose number of the requirement. Considerable input of the heat at a very high level, because you know the cracking. So, cracking, that will be endothermic, and so we need the heat. Limitation of the hydrocarbon partial pressure in the reactor, very short residence time, that is also required to minimize the development of slower condensation process, because the coke formation is because of the condensation process that is taking place, and the precursors are the aromatic compounds, because during the process and the cracking, a large number of the products we are getting. So, effective quench of the reactor effluent to fix the composition and prevent any subsequent change in the process. So, in the hot section, the next step are the quenching, because the quenching, as I told you, it may be the direct, indirect and the direct quenching. Indirect quenching, direct quenching, we are using the gas pyrolysis gasoline which we are getting, not the gasoline, but the residue which we are getting from the fractionation power that is being used for the, as I discussed in the while discussing the this part, the quenching from the after the separation of the heavier fraction of this column, that will be used for the direct quenching of the your product which you are getting from the furnace, because here it immediately the reaction that has to be stopped. So, this is the importance of the quenching that we are having. Now, after the quenching, the next important section is the compression of the light product. So, here we are also doing the caustic scrubbing and drying. As I told you, the both are very important, drying and the scrubbing of the sour gases. even CO2 that may be present, because in cracking reaction that may be formed. The scrubbing with the caustic followed by molecular CO absorption, and also H2S that may be there in the feed, and so the H2S has to be removed, the sulfur compound or the mercaptan which is present in the, that is very important. And so the huge amount of the spent caustic that is being generated in the your petrochemical complexes, and so we are going for the, we are there has been continuous effort to the how to utilize this spent was, and some of the process that is developed just like wet hair oxidation, that was developed by EIL in collaboration with the Department of Chemical Engineering, IIT Roorkee, and so that process has been commercialized also in one of the refinery. This is the, as I told you, the relative cost. Cost is also increasing if you are going from the lighter feedstock to the heavier feedstock, ethane, propane, naphtha. So, if you take the ethane 1, so the cost that will increase 1.2, 1.4, 1.5. So, sometimes we are also having the combination of ethane, propane. If the naphtha gas oil, normally the percentage of the gas oil which you are using, that is less, because of the production, the lighter gas or the olefins are less than the naphtha or the propane or the ethane. Now, let us come to the cold section of the cracker plant, because that is one of the important section where the separation of the various products which you are getting from the hot section of the furnace, that has to be separated, especially the ethylene and the propylene and these other C4 compounds also that we are separating. So, after the compression and caustic seasoning and drying the light effluent from the your hot section, that enters the cold section of the unit, which performs the separation of the various products. Here the temperature refrigeration is there, and the ethane and the propane that is being used for maintaining the lower temperature. This is the actually the complete a cracker plant, where after the cracking, that is the naphtha, then the here also this is the your ethane, propane. This part that will be only after the separation of the ethane, propane from the natural gas, fuel oil that we are adding, and after the cracking, that is the what we call the transfer line exchanger, where it is this part, that is the your steam generation is there, the indirect quenching, then direct quenching is there, and then the after the compression and the removal of the impurities, which I told you we are using the NOH scrubbing. So, spent caustic that will be there, and then the after that removal of the impurities and the your CO2 or the H2S, then it will go to the separation, where the demethanizer is there, and demethanizer gases methane that we are separating. These are the series of the fractionating column, and they are operating at different temperature depending upon the boiling point of the component. So the in case of the methane, that is around minus 165 degrees centigrade. So, from the demethanizer, the product which we are getting here after the drying and the scrubbing, that is going to the demethanizer, where the separation that is taking place, and the gas is lighter in means the gases that may be hydrogen also, methane that is separated here, and then the bottom product of the demethanizer, that is going to deethanizer. From the deethanizer bottom, again it will go to depropanizer for the separation of the propylene. From the deethanizer, the top product, which is ethylene, that is going to do acetylene hydrogenation with the palladium catalyst that we are using, and so after the hydrogenation, that is going to the for the separation of the ethylene, and the ethane, the heavier fraction, that will be again recycled to the system, and the steam which we are getting here from the deethanizer, that will go to the depropanizer, again as we did in case of the acetylenic compounds which are present, because that is the requirement of the ethylene or the propylene, which is going to be the for the polymerization. So, ethylene compound that should be very less, and so it is going to the, after the separation here, it is going the steam to the deproponizer, and from the deproponizer again this steam that is going to the removal of the steam, and with the same hydrogen in the presence of the hydrogen, and then it is going to the final separation of the propylene, and this propylene again it is going for the various uses, and the product of this propane is again recycled, and as I told you, the propane that we are using for the in the refrigeration cycle. Similarly, here the bottom of the your this column, that will go to the another column for this what we call the debutanizer for the mixed product C4 and onwards, because that will be getting, and then the pyrolysis. This C4 which will be discussing separately, the recovery of the C4 C5 gases from the cracker and the FCC, that is one of the very important feedstock for getting the some of the very important your feedstock for synthetic rubber industry, and some of the C5 they are also being used in the pesticide industry and other various chemicals, additives, and that we are making, especially in the crop protection, and cyclopentadiene, isoprene. Here we are getting the butadiene or the, so these C4 gases they are very important from the point of view the petrochemical, and the pyrolysis gasoline, that is the complementary, we are getting the steam that will go for the further processing, that can be combined with the your reformate for, and it will go for the separation of the aromatics, depending upon the process which you are having. Sometimes it may be also used as a fuel in case of the, if you are having a gas cracker and there is but if you are having the integrated part of the refinery where the reforming section is also there, so that can be combined with the reformate and for the production. So, the cold section, the hydrogen to the various concentration that may be there, ethylene containing 99.4%, 95% propylene, means that is the purity of the product which you are getting. A C4 cut containing 25 to 50% of the butadiene, because this is one of the very important product which we are producing in case of the cracker plant, that is the butadiene, and this is being recovered by all the cracker plant which is based on the naphtha, and because the butadiene that can be used for the making of the polybutadiene, or it can be used for making the SBR, styrene butadiene rubber, as Indian Oil Corporation Panipat Refinery, they are going to have the SBR, they are going to manufacture, and the plant is already under construction, and the shortly it will be commissioned. So, another product which you are getting from the your cracker plant is the pyrolysis gasoline, which is rich in the aromatic hydrocarbons. So, that aromatic that can be separated, or it can, some of the part of the pyrolysis gasoline which is having the higher oxygen number, that can be used along with the gasoline. Now, come to the each section which I discussed in the flow diagram. Demethanizer, methane condensed at the top around minus 100 degree. This is the pressure. Acetylene eliminated by selective hydrogenation. Catalyst palladium or the nickel catalyst that we are using. Basic reaction which are taking place, that is the primary cracking and the secondary cracking. Cracking of the saturated aliphatic hydrocarbons in paraffin and the olefins. Lighter products rich in the olefins produce composition will depend on the operating condition and the type of the feedstock you are having. Then the come to the separation of the demethanizer. As I told you, the steam after the separation of the methane and the hydrogen, the bottom product that is going for the separation of the ethylene. So, ethylene fractionated unreacted part of the ethane, that is recycled. then come to the, and in between that is the that is steam that is going for the removal of the ethylene compound, and after that finally it is separated. So, before going for the getting the ethylene directly, that will go first to the hydrogenation section for removal of the ethylene compound, and then it will go finally for the separation. So, depropanizer C3 cut from the bottom of the deethanizer is fractionated, C3 cut from the top of the depropanizer is selectivity hydrogenated to remove the methyl acetylene and the propylene. This is what we are doing in case of the deethanizer also. The ethylene steam that is going to the for the selective hydrogenation of the acetylene compound. Propylene contain 95% separation in supplementary column for more pure propylene. After the treatment, after the hydrogenation, that steam again it will go to the another column where the separation of the pure propylene that will take place, and the bottom unreacted propane that will be recycled to this. That is from the main propanizer column. From the bottom of the that will be recycled, and the depropanizer bottom and the first column that will go for the separation of the C4 gases. So, removal of the propane from the propylene, separation in the supplementary column for more pure propylene, which I showed you in the diagram where we are separating, and the depropanizer separation of the C4 steam from the C5 steam. Because the C5 plus steam that will be separated as the bottom product, and C4 and C5 some steam that will go to the top product, and rest will be C5 plus will be in the bottom product, which is called the pyrolysis gasoline. So, let us again revive. This is the actually I was telling about the hot section. After the hot section, that is going to demethanizer. From demethanizer it is going to the deethanizer, and they remove the top product that is going for the acetylene hydrogenation in the both the cases, in case of the propylene steam and the ethylene steam. Then it is going to the for final separation here, this another column which I was telling, and here from the ethanizer this is going to the depropanizer, and from the depropanizer this steam again for removal of the acetylene compound, and then it is finally going to another column where the propylene separation that will take place, and the propane is recycled here. Similarly, the ethane that is recycled from the this column, and the finally from the depropanizer it is going to debutanizer, the mixed C4 products, and here the pyrolysis gasoline that will be getting. So, these are the some of the major reaction via free radical mechanism that is taking place in the furnace. Primary cracking, where the initial formation of the paraffin and the olefins takes place. Secondary cracking reaction, where light olefins rich in olefins are formed, and during the process, as I told you, the other reactions are also taking place, and the aromatics are also produced, and these aromatics are the precursor for the of the coke formation. So, series of reaction, condensation reaction that is taking place, and because of that we are getting the finally the coke formation is there, and that cannot be avoided because always there will be some coke formation. Only thing, how to minimize this coke formation, because that will affect the run length of the furnace. So, now let us discuss the operating variables of the steam cracking, because depending upon the operating variables, the type of the product that you are getting, that will vary. First important is the composition of the feedstock. As I told you, we are using the wide variety thermometer from ethane, propane to gas air. So, the type of the product you will be getting, that will totally depend upon the feedstock, because the ethane, more ethylene will be there, ethane, propane, the olefin production will be higher, other residual is just like the heavier fraction, that will be less in case of the ethane, propane. In the that, and so far naphtha is concerned, that is in between the ethane, propane and the gas oil. Then the other important parameter, that is the reaction temperature. The temperature means the severity, it should not be too low or not too high, because the chances of the more coke formation will be there at high temperature, and lower temperature the yield of the lighter component olefins, that will be less. Residence time, as I told you, that is very important in the furnace. So again we will be discussing all those hydrocarbon partial pressure and the partial pressure of the hydrocarbon is steam to naphtha ratio, because the steam that is playing important role, that is in reducing the partial pressure. Then the severity and the reaction temperature, they are interrelated parameters. The various feedstock, as I discussed you, that the steam cracking or naphtha, natural gas, or it may be natural gas condensate also, and gas oil. The yield of the ethylene varies depending upon the type of the feedstock used. Ratio of the ethylene and propylene yields decreases steadily from ethane to heavier fraction like naphtha and gas oil. Pyrolysis gasoline yield increases with increase in the hydrocarbon heaviness. As I told you, in case of if you are going for the gas oil, you can crack the gas oil, you can get olefins, but the formation of the heavier fraction and the pyrolysis gasoline, that will be more than the lighter feedstock ethane, propane which you are using. The coke formation increases with the increasing heaviness of the hydrocarbons. The chances of coke formation will be more if you are using the heavier fraction. Reaction temperature. The reaction temperature involved is about 700 to 900 degrees centigrade, depending upon the type of the feedstock, because in case of the ethane, propane, lower temperature that will require. If you are going for gas oil, the higher temperature that will require, and in case of the naphtha, it is in between the ethane, propane, and the lighter hydrocarbons like ethane, propane require lower temperature than the heavy saturated hydrocarbons, which I told you. The reaction temperature involved is around 7 to 900, already we have discussed this part. Now let us come to the residence time. Residence time, again that will, residence time for lighter hydrocarbons like ethane and propane is shorter than that of the heavy feedstock like naphtha and the gas oil. So this is a very important parameter in case of operating variable in case of the furnaces. Longer residence time for heavier feedstock is required than the lighter feedstock. Residence time in the radiant section has to be carefully controlled to minimize the polymerization reaction and other undesirable reaction which is taking place in the furnace. So that is very important, the residence time, and that is a very short residence time we are maintaining in the furnace. The residence time of the hydrocarbon in the furnace varies from 0.15 to 1.2 seconds depending upon the type of the feedstock you are having. However, new breed of the furnaces have residence time as low as 0.1 second. And this already I told you, the longer residence time for heavier feedstock than the light feedstock. Shorter residence time improve the yield of the ethylene, and because if you are having the shorter residence time, yield of the ethylene and propylene, that will be more. If you are going for the longer residence time, the formation of the heavier fat, even in ethylene and propylene, if the shorter residence time, more ethylene will be there. If you are slightly increasing the formation of the propylene, that may be more. Hydrocarbon partial pressure and the role of the steam, which I was telling, because steam that is playing very important role. Pyrolysis reaction more advanced at lower pressure. Ethylene yield decreases as the partial pressure of the hydrocarbon increases. So here you see there are why we are using this steam, because that will lower the partial pressure of the hydrocarbon, otherwise yield of the ethylene that will be affected. Role of the steam, which I was telling, that the why we are using the steam, reduces the overall reaction rate, enhance the selectivity of the pyrolysis in favor of the light olefins which is desired, and increases the temperature of the feedstock. So, that is the also helping in the increasing the temperature before it is going to the cracker. As I told you, the one term, very important term that we are using in case of the furnaces, that is the operating severity and the selectivity, because this what we need in case of the cracking, that is the more and more lighter product than the heavier product. So, severity, that is the term we are using, that is defined as the depth of cracking or the extent of conversion that is taking place, and again the severity means the higher temperature we are applying the more severe condition. So, the one kinetic severity function, that term that has been given, and based on that just I will discuss in the next slide about the how much the kinetic severity function, that is the we should mention. So, maximum severity represents the acceptable optimum yield of the ethylene. At low and medium severity, primary cracking and dehydrogenation reaction predominate. They cause sharp decrease in the yield of methane, ethylene, propylene and C4 hydrocarbons, reduction in the C5 gas. At very high severity, methane and ethylene yields levels up, while those of the propylene and C4 cut reach a peak and then decline. Ratio of the ethylene and propylene yield increases with the severity, which hence favors the formation of the ethylene. Now, let us discuss the coke run length of the furnace, because as I told you, during the operation of the furnace always the coke formation. So, what are the reason for the formation of so that may be because of the sequence of catalytic and non-catalytic reaction that is taking place, gas phase and on the solid surface of the reactor, nickel and iron, because they are present in they are the material of the construction, the nickel alloy that may be there, because high temperature in the furnace we are using high nickel alloy tube we are using. So, nickel and iron catalyzes the coke. Top droplets are precursor of the part of the non-catalytic coke. Again we are having the two type of the coke that has been defined. One is the non-catalytic coke and another is the catalytic coke. Catalytic coke means which has been formed due to the because of the presence of the some of the metals like nickel and iron which catalyze the rate of coke formation is highest at the start of the pyrolysis run, when the SS tube or surface are clean, because they are coming in direct contact. After that some passivation, or you can say the coating is there, and so the always the rate of coke formation is higher at the initial stage of running of the furnace. So, what is the effect of the coke? Why we are bothering about this removal of the coke and the formation of the coke? Because the total run length of the furnace, that will depend upon the coke. If the less coke means you can increase the run length, if the higher coke formation is there, so definitely run length of the furnace that will go down. So, the coke reduces the cross section of the tube, necessitates the higher pressure. What will happen if the coke is deposited inside the tube? That will increase in the outside temperature of the tube. At the same time, the high pressure drop, higher pressure that will be required, that will reduce the heat transfer across the wall, necessitate the higher metal wall temperature to maintain the cracking temperature. So, because of that reason, because you need the higher temperature, the tube skin temperature or the outer temperature that will increase. Higher temperature application create problems with the creep accelerated by carbonization. low cycle phase. These are the some of the problem which may be there because of the formation of the coke in the tube. This is we define the furnace run length, because you see the normally the furnace run length that is very widely depending upon the type of the feedstock and the operating condition you are maintaining. That may be from the, you can say, the 25 to 50-60 days, that may be the run length of the furnace depending upon the, because that has been surveyed, that is around 40 to 50, that is the optimum run length that is considered. So, run length, this is defined as the Tm is the maximum allowable tube skin temperature, and delta Tm is the average rise in the tube skin temperature, Tmc is the maximum metal skin temperature when it is clean. So, this is the how you can determine the run length of the furnace. Now, let us discuss, because the coke formation, as I told you cannot avoid, only you can minimize, but even after that you will have to one furnace that will have to bypass if the excessive coke formation is there, because the high coke formation is there, the pressure drop and then the skin temperature of the tube, and then at the same time more fuel that will be required. So, whole operation of the furnace that will be upset. So, the decoking, that is the, we are having the two type of the decoking process. One is the mechanical decoking, where you are using the high pressure water jets and the longer time that it is required. So, steam we are decoking, that is the high temperature we are doing the decoking, where it is the cooling, spalling and the thermal shocks and the coke and break away from the tube surface and packed by the steam. Burning, decoking without air, injection of the steam and air, higher time is required and higher temperature is required. Now, let us discuss about the development which has taken place in this steam. You see, there has been continuous development in the steam cracking process, especially in the furnace design. From very low, you see, in India we started only with the 20,000 ton capacity ethylene cracker, first cracker plant, which was started by Union Carbide in Bombay. So, that was the lowest capacity. Then we started 60,000, 1,000, then it was 1 lakh ton capacity IPCL, and then the new breed of the furnaces which you are having, just like we take it with Reliance or the Panipat refinery, 8 lakhs ton capacity. So, the what are the parameters that has been considered in the development of the cracking? Because one of the basic, because you see the whether you are going in the petrochemical complex, any operation, or in case of the refinery, a very appreciable amount of the cost, operating cost, is in the form of the energy. So, the high heat level, heat recovery, waste heat utilization, that is very important factor while going for the better design. High and relatively constant ultimate yield of the ethylene, ability to process higher sulfur feedstock, higher hydrogen production, ability to crack byproduct ethane and LPG mixture. Because now the even in case of the ability to higher sulfur feed, and at the same time the variation, the higher hydrocarbons, means the gas oil cracking. Now, we are talking about the gas oil. Even in case of the steam cracking, now the development that has been the catalytic cracking to reduce the temperature and to improve the selectivity of the reaction towards a particular more ethylene or the propylene. So, in future we may have the just like the FCC, here also the catalytic cracking process, which will lower definitely the temperature, and at the same time that will also the purity of the product that will be better. So, these are the some of the actually the major development that has taken place, which I told you, the increased capacity and the severity, improved selectivity. Severity means the optimum severity in the term of the kinetics, that is around 3 to 3.5. That is the severity, kinetic severity function, that the kf that we are maintaining around 3 to 3.5. Improved selectivity, higher thermal efficiency, rapid temperature rise of the feed, higher exit temperature, shorter residence time. You see the why higher exit temperature means the less coke formation is there. So, the temperature definitely will be higher. If the more coke formation is there, temperature that will go down. So, we can control the temperature also from the outer skin temperature of the tube and then the exit temperature of the gas. The coke thickness in the tube is function of on stream time and the severity of the cracking. Analysis of the coke samples, because you see the why this function of the stream time, because residence time and the temperature that you are maintaining depending upon the formation of the coke, that will vary. So, analysis of the coke sample that has been done. So, the coke samples contain iron, nickel, chromium extracted from the metal wall or the coil, because lot of the corrosion problem is also there in the furnace. Because the high temperature is required, as I discussed earlier, because some of the problem of the high temperature corrosion is there. The coke form catalytic contain metals and served as a site for the non-catalytic coke. Catalytic coke most prevalent on and near the surface. So, that is the catalytic coke and non-catalytic. Decoking, how to remove the, because one was the mechanical decoking, but the use of the additives which passivate the reactor walls, addition of the sulfur compound to the feed. So, we are having the two types of the organic compound which has been actually all the various R&D division after the study, they have found that the organophosphorus compounds and the some of the sulfur compounds, the triphenyl phosphate, benzyl diethyl phosphate, ditriethyl phosphate, thiopene, dibenzyl sulfide, benzyl sulfide. These are the some of the sulfur compound and the organophosphorus compound which can be added to reduce the coke formation. Depositing of the silica coating on the tube side, so that the, because I was telling the iron and nickel, they catalyzes the coking reaction. So, this already I discussed about the one of the point which I told you, the increasing the furnace capacity, increasing the cracking ethylene selectivity, because that is our more interest, but now in the future it may be the requirement of the propylene as increasing. So, it may be the now the two thoughts are there whether we are operating at the ethylene or the propylene mode, because the ethylene earlier the ethylene was called the king of the chemicals, propylene that was the crown prince, but now the and sometimes the usage of the propylene is more than the ethylene. Reducing the downtime of the decoking, because that is also very important, because normally what is happening after certain turn length, when the excessive coke formation is there, the furnace is bypassed for the removal of the coke, and then the, so that downtime that has to be avoided, reducing the maintenance, because this is also one of the important factor which affect the overall running of the furnace. These are the some of the development which has taken place just to improve the efficiency, quench and heat recovery system, cracked gas treating system, then the highest ethylene yields, broadest liquid feed flexibility, means now the you should operate with the, just like I told you the cracker plant of the Reliance, that is the both multi-feed. We can use the naphtha or you can use the gas also. Reduce feedstock consumption, byproduct ethane and LPG mixture, that can be, if you can use the LPG also, the, because what is happening now the LPG is this, many of the places the LPG is surplus. So, that LPG also can be because this is the mixture of the propane and butane. So, that can be also cracked. So, just to summarize, this is the development, lower energy consumption part of the ethylene. The present specific energy consumption figures have reduced by more than 50% as compared to the mid 70 figure, because you see the capacity which I told you, that is the 20,000 to 60,000 to 8 lakhs ton capacity. So, this has been the major development has been in the what are the various area where the major development are the fire heaters, compressor, heat exchanger, fractionating count. Improved overall yields of the ethylene by short residence time, higher severity, because as I told you earlier, the tube diameter was used to be more. If you are increasing the tube diameter or decreasing the less tube diameter means your velocity will be more, less residence time will be more ethylene will be there. If you are having the high diameter, the more propylene will be there, and the higher severity means severity around 3.5, that is the optima. If you are going beyond that or less than that, then both are going to affect the product yield. So, in case of the furnace, some of the other development, especially from the coke formation point of view and the corrosion point of view, has been the development in the decoking process to have higher run length with use of additives, development in the pyrolysis furnace alloy material to provide efficient and reliable performance with minimum maintenance, because you see that is the one of the problem in case of the refinery and the petrochemical complex also, because you are using the large number of the furnaces, and so the corrosion problem is severe if the feed is not properly treated or the removal of the sour gases is not there properly. So, catalytic pyrolysis of the naphtha, this is why I was telling. Now, what we are talking about the catalytic pyrolysis of the naphtha for increasing the plant flexibility as well as reducing the required temperature and coke deposition for a given conversion, because this is the one of the very important, and in the future now we may have the catalytic pyrolysis of the naphtha, so that the we can choose the catalyst and with a particular selectivity towards a desired product. So, this is the what the future development that is going to take place, and the flue gas heat recovery, because what we are doing, we are the gases, they are coming at a high temperature and we are doing the quenching or the direct or indirect. So, temperature that has to be reduced, and from high temperature to low temperature we are going for the separation. So, the improve in the gas heat recovery system, that is very important. Increased feed stock flexibility, which I told you, that has been the one of the actually the again development in the furnaces, the possibility of cracking more than one type of the feedstock in the same furnace. The advanced cracking reactor ACR, which we call it, the process offers total liquid feedstock flexibility from light naphtha through the vacuum gas cells in the same production unit. So, this is the, as I told you, the gas and naphtha. Now, we are talking about the naphtha and the gas oil, both can be cracked in the same furnace with a better efficiency. So, this was the about the naphtha, the gas cracking, which is the heart of the petrochemical complex and the large number of the important product we are getting, especially the olefin and the pyrolysis gasoline as a complementary. So, in the process, as I told you, the separation of the C4, C5 gases, because so for the ethylene and the propylene is that is their main product. So, many of the refinery earlier they were not separating the various byproducts. One is the butadiene, another is the your isobutylene, or it may be the butene 1, butene 2, isobutane, all those products that we are getting there in case of the, because the Now, requirement of the MTB, the oxygenates or the TAM or the requirement the isoprene for rubber manufacture or the butadiene for the rubber manufacture is there. So, we can go for the separation of the C4, C5 gases, which we will be discussing in the next lecture, that is on the upgradation of the C4, C5 gases of the naphtha cracker or the steam cracker and the FCC.